Have you ever really stopped to think about numbers? I mean, not just, using them to count your change or something, but what they actually are. We use them every single day, but just beneath that simple surface is this incredible, fascinating universe, but layer by layer to solve problems that at one point people thought were totally impossible.
And that's really the big question we're tackling today. We're going to go on a journey to see how mathematicians, whenever they hit a wall, a problem they just couldn't solve, they didn't give up. No, instead they invented entirely new kinds of numbers, literally expanding the universe of what was possible. Okay, you ready? Let's dive in. So where do we even begin? Well, our journey starts at the most intuitive place you can imagine, with the very first numbers humanity ever needed. You know, the ones we use to count stuff.
These are the natural numbers, and you'll often see them represented by the letter n. They start with 0, which you can think of as, well, nothing to count, and they just go on forever. Now, this set was formally described by an Italian mathematician named Giuseppe Peano, and he realized you could build this entire infinite set from one really simple idea.
Peano's brilliant insight was this concept of a successor. It's so elegant. You just start with 0, the next number, its successor, is 1. And the successor of 1, that's 2. And so on and so on. Every single natural number is just the successor of the one that came right before it. It's like this simple process gives us an infinite ladder of numbers to climb. So, what can we actually do in this world of natural numbers? Well, we can add them, and the answer is always another natural number. We can multiply them, which is really just a fancy way of doing repeated addition. And again, the answer is always a natural number. We say these operations are closed. But what happens when we try to subtract a bigger number from a smaller one, like 2 minus 5? Suddenly, we hit a wall. We're stuck. There is no answer to this question inside the universe of natural numbers. It's our first impossible problem. So to solve this, we can't just find a new number. Nope. We have to invent an entire new dimension for our number line. We have to introduce a negative space. And welcome to the integers. You'll see them represented by the letter Z, which comes from the German word Zahlen. It just means numbers. This set includes all the natural numbers we already know and love, but it also includes this perfect mirror image of them on the other side of 0, the negative numbers. The real key that unlocks this new universe is this one powerful idea, the additive inverse. All it means is that for every number, there's a perfect opposite. The opposite of 3 is negative 3. The opposite of negative 5 is positive 5. It creates this perfect balance where any number added to its opposite just cancels out and takes you right back to 0. And just like that, with this new tool, our impossible problem just vanishes. 2 minus 5 isn't a paradox anymore, it's simply negative 3. By inventing the integers, we've made subtraction a closed operation. Any integer minus any other integer will always give you another integer. Problem solved. Or is it? See, we've conquered subtraction, but a new challenge pops up almost immediately. I mean, sure, we can divide 4 by 2 and get 2. That's an integer. But what happens when we try to divide 3 by 2? Uh-oh. Once again, we're stuck. The answer is not in our set of integers. We have another impossible problem on our hands. So, you guessed it. It's time to expand our universe again. If whole numbers aren't going to cut it, we need to be able to talk about all the pieces in between them. And this brings us to the rational numbers, represented by the letter Q. The name itself gives you the solution, ratio. Every single number in this set is just a ratio of 2 integers. And suddenly, our impossible problem of 3 divided by 2 isn't impossible at all. It's just the number 3 over 2. With this amazing invention, division becomes a closed operation. Well, with one very, very famous exception, we must never, ever divide by 0. You know, one of the coolest things about rational numbers is their flexibility. The same exact value can wear a bunch of different costumes. The number 1/2 can show up as the fraction 1 over 2, or as the decimal 0.5, or even as an equivalent like 50 over 100. Other rationals, like 1/3, show up as decimals that have these infinitely repeating patterns. They might look different, but they're all part of the same very versatile family. So let's take a step back. We've built a system that can handle addition, subtraction, multiplication, and division. It really seems like we've filled in all the gaps and our work here is done. Surely our number universe must be complete now, right? Well, you probably saw this coming. No. In fact, the ancient Greeks stumbled upon a discovery that deeply, deeply disturbed them. It shattered their whole philosophy. See, they believed the universe was perfectly ordered and that everything could be explained with whole numbers and their ratios. But then they found numbers that just defied that logic, numbers that can't be written as a simple fraction, existing out there, beyond their rational world.
These are the irrational numbers. Their decimal forms go on forever, just like some rationals, but, and this is the crucial part, they never repeat in a predictable pattern. You're probably familiar with the celebrities of this group: pi, the ratio of a circle's circumference to its diameter, Euler's number, e, and the square root of 2. None of these can ever be pinned down as a simple fraction. And this is what we mean in practice. Pi starts 3.14159, and it just keeps going and going with no pattern forever. It's a number that is very real. We can use it in calculations, but we can never ever fully write it down. So, to create our final complete set for this journey, we do one last big expansion. We take all the rational numbers we have, and we unite them with all of the irrational numbers. And this gives us the set of real numbers, which we show with the letter R. This is it. This is the complete continuous number line you learned about in school, with absolutely no gaps or holes whatsoever. So we did it. We've built our universe, the complete set of real numbers. But a universe isn't just about the stuff inside it, it's also about the laws that govern everything. Now that we have all the numbers, we need to agree on the fundamental rules of how they interact, a kind of universal grammar that makes sure our calculations are always consistent and true. Let's start with powers, or exponents. They follow a few simple but incredibly powerful laws. So to multiply powers that have the same base, you just add the exponents. Easy. To divide them, you subtract the exponents. To raise a power to another power, you multiply them. And even a negative exponent has this elegant solution. It just means you take the reciprocal. These aren't just random rules to memorize. They're the essential shortcuts that let us navigate this number universe. But what about when you have a whole mess of different operations in one expression? You got addition, powers, multiplication. How do you know where to even start? Without some kind of standard order, you and I could look at the same problem and get totally different answers. That's why we have a universal grammar for math. And this agreed-upon hierarchy is the order of operations. At the very top of the pyramid are any grouping symbols, like parentheses. We always solve what's inside them first, no matter what. Next up, we handle any exponents. After that, we do a pass from left to right, doing all the multiplication and division as we see them. And the very last pass, again from left to right, takes care of all the addition and subtraction. Do that, and you get the one single correct answer. So let's see this grammar in action with this monster of an expression. Now, it looks chaotic, but the rules give us a clear path forward. We'd start inside the parentheses, right, like that 3 minus 5. Then we'd resolve all the exponents, being really careful about how parentheses change the game for something like -2 to the 4th power. Only after all that is done would we handle the multiplication, and finally the addition. The key takeaway here isn't the calculation itself. It's knowing that by following this exact order, every single person who solves this problem will arrive at the exact same unambiguous answer, -13. It's a system that guarantees we're all speaking the same language. So, we've journeyed all the way from simple counting numbers to the complete real number line, expanding our universe every single time we hit an impossible problem. We built this incredible system to describe the world around us. But this journey really begs one final question. If every problem led to a new dimension of numbers, what other universes, built to solve even stranger problems, might still be out there, just waiting for us to discover?